Modern data systems often fail under the weight of predictable structural misalignments, where rigid architecture is forced to carry a workload it wasn't built to sustain. Yet when these breakdowns occur, engineering teams lack a shared vocabulary to diagnose the issue. Instead of identifying the architectural flaw, they often rely on competing vendor-specific error logs that describe symptoms rather than the root cause. The datatsm framework operates on a single doctrine. A data problem without a dimension is an observation without a diagnosis. To understand how to diagnose these systems, we have to break the datatsm model into its three constituent parts. Data represents the actual payload, the digital representation of real-world entities, financial transactions, or user events flowing through your system. The T represents 7 specific structural dimensions used to categorize technical and organizational issues. These range from truth and time to technology and the team. And the suffix ism represents the vendor-neutral diagnostic doctrine used to evaluate those dimensions across any stack. Systems fracture when an organization shifts operational mechanics, for example, moving from nightly batch reporting to live streaming, but leaves the underlying architecture locked in legacy patterns. This is the T7 workload analysis matrix. It serves as a diagnostic map, plotting 6 major workload archetypes on the y-axis against the 7 structural T dimensions on the x-axis to identify exact failure points. Without this structural map, engineers diagnose the exact same failure using different terms, which can lead to misaligned vendor lock-ins and architectural friction. We start at the baseline, operational OLTP workloads. Here, truth is strict, relying on binary, row-level ACID correctness. It's entirely committed or rolled back. This dictates the technology dimension, requiring row-oriented storage and B-tree indexing for integrity. This structural alignment serves point-of-sale or core ERP systems, where financial state must be immediately and perfectly consistent. Watch the shift to analytical OLAP. Truth becomes a synthetic, reconciled domain truth, built by aggregating millions of rows. This forces the technology layer to vectorized engines and columnar formats. Massive aggregations require layouts like Parquet and SIMD bitpacking, scanning columns instead of individual rows. If a data team attempts to execute heavy, multi-stage ELT joins on a legacy row store architecture, the system often faces performance degradation. The database expends memory traversing unrelated column data in a row, leading to increased read latency and active transactional lockups. Analytical bottlenecks are rarely hardware failures. They result from dragging an OLAP workload across an OLTP dimension. This structural friction heavily increases when the architecture moves from bounded batch processing into the continuous, rapid flow of unbounded streams. The critical friction point in a streaming workload happens in the time dimension. Streams process an unbounded flow of events that frequently arrive out of chronological order. Managing this requires event time watermarking, allowing the system to wait for late-arriving data before finalizing a temporal window. This temporal shift breaks legacy models, requiring an update to traceability. Traditional lineage fails because it's difficult to map a static start and end for a job that never finishes. Traceability here means tracking message offsets and distributed trace IDs across Kafka brokers. A system's ability to guarantee a record is processed exactly once relies on reading and committing those offsets accurately. Stream processing relies on continuous momentum, ingesting and transforming state in flight. Attempting to govern this with batch-time tools compromises data freshness and state consistency. We reach the most complex edge of modern data architecture with wide-table AI feature engineering. Machine learning workloads test both trust and transformation. AI trust requires feature reproducibility, guarding the exact training dataset against data leakage. Meanwhile, transformation shifts to compute-heavy matrix math, using hardware-aware formats for zero-copy handoffs directly to GPUs. The absolute extreme occurs in vector search and retrieval-augmented generation. Here, truth is no longer an exact database match. Vector truth is based on contextual semantic fidelity, measuring mathematical distance in a multidimensional space to find concepts that cluster by meaning. Because of this, traceability must now connect a mathematical vector coordinate backward to the specific chunk of source document text that generated it. If trust controls are not updated to manage this specific architecture, the system becomes vulnerable to document context window leakage and prompt injection attacks. Maintaining stability across these cognitive workloads requires specialized hardware indexes and embedding generation pipelines. Deploying this cognitive AI on legacy transactional dimensions can lead to severe hallucinations and outputs that simply cannot be verified. We can now see the entire scope of the T7 framework. By tracking this matrix, you can map the architectural drift from classical operational systems down to modern cognitive AI. This illustrates the datatsm diagnostic principle. Architectural friction occurs when a workload's mechanical requirements diverge from its dimension's capabilities. Cross a streaming workload requirement with an OLAP technology dimension, and the system fails. The framework isolates this friction point, turning an ambiguous outage into a specific architectural diagnostic. Datatsm replaces vague system complaints with a specific diagnostic language for evaluating and governing data architecture. It provides the map needed to evaluate your own architecture and locate hidden breaking points before they lead to failure. So, looking at this matrix, which primary workload class in your architecture is currently experiencing the greatest diagnostic friction?